In this video, we are going to learn how to perform two-factor analysis of variance in Excel. Uh, in particular, we are going to focus on three things: how to perform analysis of variance, number two, how to perform residual analysis, and number three, how to perform post ANOVA comparison of means. And we will focus on the Tukey test. Now, as you already know, you can use different statistical software to perform this analysis. For example, Minitab can do this easily. IBM Spaces you can use Jump. There is another software called Design Expert. But the problem is, most people, they may not have access to this advanced statistical software, and everybody has access to Excel. So it would be good to understand how to perform this in Excel, because there is in Excel, one thing, it is widely available. Second thing is, because everybody is familiar with Excel, it's not the learning curve is not that steep, right? So let's discuss this problem here. This is the problem that we discussed in the previous video. We looked at the results and analysis and conclusion of from, and we looked at the results from various software. Now we have an opportunity to perform the same work in Excel. So this is basically a battery life problem. We are interested in studying the effect of material type that is used in the battery plate and the temperature, atmospheric temperature. These two factors, how they affect the life of the battery. So we are using three different. We have a choice between three different material type to use for the battery plate, and let's call them material type 1, material type 2, and material type 3. And we're going to perform the test at three different temperatures: 15 degree Fahrenheit, 70 degree Fahrenheit, and 125 degree Fahrenheit. And as you will notice that uh, we performed four experiment: one, two, three, four experiment at each combination of material type and temperature. So our sample size is four, right? Our We have two factors. One factor is material type, second factor is temperature. Each factor has three levels. Material type has three levels, temperature has three levels. Our sample size is four, and the total number of experiments performed is, as you can see, first of all, there are three times three, nine combinations, right? Nine unique experiments at unique settings we can perform, and we are performing four experiments at each unique combination of the two factors. So total number of experiments will be 9 times 4, 36. And what we have here is the battery life in hours: 130 hours, 34 hours. For each of those experiments, we measured the battery life, and that is listed here. So we have the data. Now what you need to do is, in Excel, you can click on Data tab, and in Data tab, you have something called as Data Analysis option. Now, if you don't have that option, what you need to do is you need to go to File, then go to the Options, then Add-ins, and here we have to add in the analysis tool pack. So I'm gonna select this analysis tool pack, and maybe you even want to select analysis tool pack VBA, but I think the one is just enough. Then after selecting that, you need to click on Go, and uh, it has these options that you can choose in analysis tool pack VBA, and click OK. Since I already have it installed, I don't need to do that, but that's how you can access data analysis toolpack in Excel. Now, so let's click on that. Okay, and here we have different statistical analysis or statistical tests that we can choose from. So I'm going to choose. Uh, we have two factors, so I'm going to choose uh, ANOVA two factor, but we have two options: ANOVA two factor with replication and ANOVA two factor without replication. So which one should we choose? Without replication means the experiments are not repeated more than once at the same setting. There is sample size of one, but in our case we do have replication. We performed four experiments at the same setting. Our sample size is four, so we have two factor with replication. So I'm going to select that. And one other thing, before I go on and perform this, I want to say, just take a look at how the data is displayed in this table. We have these column headings, and then we have row headings, right? This cell here is blank, and then we have this observation. So you have to make sure your data is organized in such a fashion that Excel can understand what's going on, right? So I'm going to select with replication. Okay. So our input range for the data, so that's going to be this here. Okay. Rows per sample, how many rows we have per sample? One, two, three, four. I have color coded them in different colors just to make it easy to understand. So there are four rows per sample. Now alpha value is 0.05 or 5%. That's the that's the value we mostly used, right? 95% confidence or 5% alpha level. So I want to keep that same default. Then let's see where we want to put our output, where we want to display our ANOVA output. So I'm going to select the cell. Maybe I want to put it somewhere here, G1. Okay, I'm starting from there. And okay, so here we have the results of our analysis of variance. Now let's try to make sense of these results. First of all, it says summary, and the Excel gives you a nice statistical summary of the data. For example, material type 1 and temperature 15 degree Fahrenheit. How many experiments were performed? Count is 4. What was the sum of all these four numbers? Is 539. What is the average of those numbers? What is the variance? And same for 70 and 125 degree Fahrenheit. And then we have the total. How many total experiments were performed for material type 1? It's 12. And then sum of all those observations, their average and their variance. And then same we have for material type 2 and material type 3. And finally you will see the total across each temperature. If we want to summarize the data for each temperature, for example, for 15 degree Fahrenheit, we performed 12 experiments. Then the sum of those observations, average and variance, same idea. So now we are talking about these 12 experiments, right, under 15 degree Fahrenheit. When you say 12 here, we are talking about these 12 experiments, that is for material plate 1. So it's a two-dimensional, the data is presented in two dimensions. So this is good. We don't have to calculate these things now. And finally, what we are interested in is the actual ANOVA table. So let me scroll a little bit here. So let's take a look. Source of variation. So the total variation in the data, total variance or variation in our data uh, is divided in three uh, three different groups. First of all, let's take a look at the different columns in the ANOVA table. So we have source of variation, then we have sum squares column, we have degrees of freedom column, mean square, which is basically sum square divided by degrees of freedom is mean square, and then we have calculated F statistics and the associated p value, and then we have F critical value, that is the value at alpha is equal to 0.05, right? that is F critical. So we can compare our calculated F value with F critical. And so those are the columns. And for rows, we have the sample, which is basically sample means I think that is we're talking about material plate, right? So I'm going to change that. So one source of variation in our data is material plate. Second source of variation is the variation caused due to different temperature conditions. So temperature, right? So we have the main effect of two factors, material plate and temperature, and then interaction effect between material type and temperature. Material type and temperature interaction effect. Okay, and within that means within each group, within, like for example, when the material type is 1 and temperature is 15, uh, because we are using the same material and conducting the experiment at same temperature, we expect to get the similar battery life. In fact, we expect to get the same battery life, but we still have some variation within that group, right? Within this group, why is that variation? Why one time you perform experiment you get 130 hours battery life, for another battery you got 74 hours battery life? Because there is a variation caused due to all other variables that are not under active consideration. We have not separated them out. For example, the variation caused by the operator performing the experiment. If two different operators are performing these four experiments, maybe there are operator to operator variation. Uh, Maybe there is a humidity, different humidity conditions, all kinds of noise or error can create this variation, right? So that is just another source of variation, which is within, or we can call it error. So now, and then there is a total, right? The total of all these four sources of variation is the total sum square. Degrees of freedom for material type, because there are three material types, so 3 minus 2 is 2. Temperature degrees of freedom, again there are three settings for the temperature, so 3 minus 1 is 2. The interaction effects, basically the multiplication of the product of these two degrees of freedom, 4. Total degrees of freedom is the total number of experiments, which is 36 minus 1, 35. And degrees of freedom for the error, you can subtract, you can first add these three and then subtract from 35. Whatever is left over is your error degrees of freedom. Mean square, and you don't even have to do all these calculations because Excel is automatically generating this data for you, right? Now mean square is sum square divided by degrees of freedom, so we have that. And the F statistics is basically mean square uh, for material type. For example, if we want to find the F statistics for the first row, which is material type, so that would be mean square material type divided by mean square error. So we want to see how significant the variation due to material type is as compared with the variation due to error, right? So putting that in numerator and putting the ms error in the denominator gives us a nice ratio, which is basically F statistics. And then we have associated p value. So now, is this factor significant or not? uh, that we need to say that, right? So let's see. We can actually write a formula here. If first let me explain the concept and then we can formalize it. So You compare your F value with F critical value. If your F value is higher than F critical value, then you should reject the null hypothesis. And null hypothesis is always about equality of means. That means we are saying that the average battery life due to material type 1 is equal to average battery life due to material type 2 is equal to average battery life due to material type 3. Mu1 is equal to mu2 is equal to mu3, right? For the material type we're talking about. So that is always null hypothesis, is always equality of means. And alternative hypothesis is basically at least there is one inequality. That means at least one material type is producing a different effect in the battery life. At least one. All of them can be different from each other, but we are seeing at least one inequality. That means at least one material type is different in its effect on the battery life. So that students get, I have seen over the years, student gets a lot of confusion in this last point. Like, what does that mean? What does F? How to compare this, right? And again, they get confused between null hypothesis and alternative hypothesis. Null hypothesis is always about equality of means, and alternative hypothesis is at least presence of one inequality. At least one factor level is different. And when you reject null hypothesis, that means the factor is significant. That means there is a significant differences in battery life due to factors. So again, students get confused with this understanding this concept, but hopefully after watching this, it will be clear to you. So that's one way, right? If F is higher than F critical value, that means null hypothesis of equality means should be rejected. That means material type is a significant factor. It's significant. It produces significant variation in battery life. Same thing can be said about the temperature. If F value, so for material type, what do you see? Yes, our F value is higher than F critical. That means material type is a significant factor. How about temperature? The temperature F value is also higher than the F critical value for the temperature. So yes, temperature is a significant factor when it comes to the battery life. And the interaction effect between the material type and temperature is also significant. It may not be as significant as the main effects of the factors are, but it is still higher than F critical value. So uh, that is significant. Other way to look at this is p value comparison. We compare the p value with alpha value of 0.05. If p value is smaller than alpha value, then we get the same conclusion. So basically, when we observe that f value is higher than f critical, we'll automatically see that the p value is less than alpha value of 0.05. So we can compare p values and come to the same conclusion. So this is 0.0019, definitely less than 0.05. So the factor is significant. This is almost 0, 1.91 times 10 to the power minus 7. It's almost 0, right? So less than 0.05. Again, temperature is, that means significant. And interaction effect is zero point zero 0.01. It's less than 0.05 again. So significant. So if we want to codify this significance test, so you can say here is equal to if, and we'll do uh, p value comparison, right? So we say if this value is less than or equal to 0.05, that means the factor is significant, right? If the condition is not true, if this p value is not less than or equal to zero point zero 0.05, that means factor is not significant. Okay, and so that will tell us whether the this particular factor material type is significant or not. And then we can autofill for the other two factors, temperature and interaction, and all three factors are, as you can see, they are significant. So that's the first part. That's basically analysis of variance part. Now the second part is to perform residual analysis. So the idea here is our analysis of variance is the statistical model that we used is based on the assumption that the residuals, the errors in the data, they are normally and independently distributed with constant variance. So once again, the results of this statistical model are based on the assumption that residuals are normally and independently distributed with constant uh, variance. If that assumption is violated, if that assumption is not true about the underlying data, that means the results of our analysis of variance cannot be reliable, right? So let's check that assumption on residuals. So to do that, I'm going to open a new sheet here, and I have to organize the data in a little different fashion. So let me do that. Let's organize the data in a different fashion. So I'm going to write the first column for material type, second column for temperature, third column for battery life, actual battery life. Okay, and fourth column, battery life predicted, predicted by our statistical model, right? Battery life mathematically predicted, and after performing the experiment, what actual battery life we observed. So material type, uh, there is one, and we have four observations. So I have to write that one four times, right? Then two four times, three four times. So that's material type, and the actual battery life that we observed after performing the experiment is these values, right? So I'm going to copy them and paste it here as a value so we don't get those color coding. So that's actual battery life, right? Then while we are at it, why don't we go ahead and copy these other battery lives, copy here. And we need 36 rows because we have 36 observations. So I'm going to copy this here. Then we have this third row, third column, copy and paste it here. So that's the 36 observation, right? And of course the material type, this pattern will repeat for the next 12 observations and for next 12 observations. Okay, so we got that. Now let's see temperature. For first 12 observations, what was the temperature? Temperature was 15 degree Fahrenheit. So we'll have to repeat that 15, and we have to repeat that 12 times. For next 12 experiments, the temperature was 70 degree Fahrenheit. So we have to repeat that for next 12, and Then we have 125 degree Fahrenheit. Okay, so we are going to repeat that also for 12 times. So you will see that we have um, for 36 observations, we have correctly noted the material type and temperature combination. We shouldn't make any mistakes in this data entry. Otherwise, uh, one mistake and everything will be wrong in future calculations or in our plots. So looks good to me. Now, what about the predicted battery life? What battery life the mathematical model is predicting for material type 1 and temperature 15? So I guess that would be the best guess. Like for example, if we perform another experiment with using material type 1 and 15 degree Fahrenheit, what battery life do we expect from that experiment? So best guess would be average of these four, right? The average, basically we already performed four experiments, and what is the average of those four experiments is the best guess for another if we perform a new experiment at that setting. So those are our predicted uh, life, right? So let's see where can I find that information. So for 1 and 15, average is here 134.75. So I'm going to copy that, okay, and paste it here. But it's the same for next four because the same combination, right? We are expecting the same battery life. So if we repeat an experiment with material type 1 and temperature 15 degree Fahrenheit, we expect that the battery life will be close to 134.75. Then for the second combination, material type 2 and temperature 15, let's see, we have material type 2 here, right, and temperature 15. So this average here, control C, that is for the next four experiments. Then for the next material type 3 and temperature 15 is this value here, 144. So let's put it for next four. Then material type 1 and 70 degree Fahrenheit, which is material type 1 and 70 degree Fahrenheit. So this average, that is for next four observations. So now I think by now you got a hang of it. Next is material type 2 and temperature 70 degree Fahrenheit. So that average for next four, then this average for next four here, then what is the next combination? 1 and 125. So that would be 1 material type and 125. So this average, that is for next four. Then material type 2 and 125 degree Fahrenheit, that average of the four observations. And finally the last one here, 85.5 for these four observations. So our table is now ready. We have the material type, temperature, battery life actual, and battery life predicted. So the errors, now we need to generate the error terms. So again, as I said before, we are checking the assumption that our residuals from this data, they are normally and independently distributed with a constant variance. So first we need to calculate residuals errors. Residual error or error, that means what is the difference between actual life and predicted life. So predicted was 134.75, but when we actually conducted the experiment with this setting, we got the battery life of 130. So the difference between the actual and predicted is residual. So equal to actual life minus predicted life. So those are our we will have 36 residuals uh, for 36 observations, and then we need to check the assumption on those residuals. So I'm going to just autofill this. So we got the residuals, right? Next thing, what I'm going to do is, for ease of analysis, I'm going to convert this raw data in an Excel table. So I'm going to click somewhere in the data. You shouldn't be here. You should be somewhere inside the data. Then go to insert and table. Then Excel will ask you where is data for your table, and it automatically selected this data. You just have to make sure that what Excel has selected is appropriate. Yes, it does look good, right? My table has headers. Yes, our table has this headers, right? Column captions. So that box is checked, and okay. So now this data is converted in Excel table format, which will help us to just sort or filter things if as needed. Next, so one assumption is about normality, right? Normality of the residuals, whether the residuals are normally distributed. So to check that assumption, we want to make a normality plot. To do that, first we have to calculate the cumulative probability of for each of these residual points. So to do that, uh, what you need to do is create a couple of more columns. So first is sort order column, and I will explain to you what this is. So we have to first sort our residuals from in ascending order from lowest to highest. So I'm gonna select, uh, click on this tab here, sort from smallest to largest our residuals. So I'm gonna do that. Okay. And so as you can see, minus 60.75 to all the way some positive values, 45.25. So we have quite a range there. And then you can give sort order like 1, 2, 3. We are giving them sort order to these residuals. And then you can of course continue the pattern up to 36. Okay. Next, you want to calculate uh, cumulative probability. And we will calculate cumulative probability in percentage terms. So percentage cumulative probability. Okay. Percentage cumulative probability. Uh, so the formula for that is equal, uh, parenthesis, sort order. It's the same, always same formula for all different problems. It's a sort order minus 0.5, always, right? Sort order minus 0.5, parenthesis closed, divided by total number of observations. So we have total 36 readings. So divided by 36, and we since we want this in percentage terms, we can multiply by 100. So that's the formula. And here we are, right? One thing to look out for is, since the cumulative probability starts with 0 and ends with 100%, we want to see that our percentage cumulative probability here is in ascending order, starting from close to 0 to all the way up to 100, close to 100. If we have numbers higher than 100, then there's something wrong, right? Or we have negative numbers here, there is something wrong. This is percentage cumulative probability. it should vary between 0 and 100%, or 0 and 1 if we don't multiply by 100. So this looks good. So now we can make the normality plot for our residuals. So to do that, select these residual columns. Okay, and then using your control key, press and hold, you can select the percentage column. Okay, and we want to make a plot, so you go to insert plot, and you can select the scatter plot. Okay, so uh, we can do a couple of things, organization to this chart here. So first of all, chart title is normality plot. Normality plot of residuals. Okay, then this y-axis is at, first of all, the as you know, the cumulative percentage probability should be from 0 to 100%. This scale, we can have the upper limit 100 there, right? So I'm going to modify my y-axis. Double click on that. Let's see, the maximum value I want 100. So that's one thing. Okay, and we want our, if the y value is crossing x value, x axis, y axis is crossing x axis at 0, but if we want to put it to the left, we can do that as well. So I'm going to double click on x axis. Let's see, I'm going to double click on x axis, and here I say vertical axis crosses the x axis at, let's see, instead of crossing it at 0, we can make it cross at minus 80. So that's good, right? Then let's see, we can add the axis titles. So I'm gonna go to the chart design, and from the quick layout, I'm going to select uh, the first option here. Okay, so we can write the axis titles here. So here on y-axis, it's a percentage cumulative probability, right? On x-axis we have residuals, and let's see, we don't need this series one here. So this is our normality plot of residuals. Now we plotted this chart to check the assumption of normality. So how do we do that? If I add a trend line from this data here, add a trend line. Okay, and you will see that most of the points, ideally all the points should fall along this straight line. If we put a thick pencil on this line, all the points should hide under that pencil. A good thick, very thick pencil, if we put on this line, all the points should hide under the uh, line. When that happens, we can say that normality assumption on residuals is checked, right? Is validated. It's valid. The residuals are truly normally distributed. Now we do have some problems in this data. For example, we have a presence of outlier, a couple of outliers, and uh, that seems to be related to some outliers in our data. So the way to look at it is we can further analyze these experiments and see why we got some outlier battery life at those points, and maybe there was some error during those experiments. So we can fix those things, right? Well, another thing we can do is x-axis is crossing y-axis at 0. We can make it cross at minus 4t. So if we go to double click on y-axis and say horizontal axis crosses y-axis at, instead of 0, say minus 4t. Okay, so now this is perfect. So this is how you check uh, the normality on residuals, and conclusion in this case is, for most part, normality of residuals assumption is valid except for the presence of couple of outliers. So that is one assumption we checked, right? Now let's check the assumption of constant variance. So we have to uh, make a few plots, and I think some of the plots I will show you here. So we just checked this plot here, right? The residual normality of residuals. Now another plot we can do is residuals versus predicted, then residuals versus material type, residuals versus temperature. And what we are looking in this plot is we don't want to see any pattern. Pattern means, like, for example, funnel shape, uh, funnel shape like this. If we see pattern like that, that means the constant variance assumption will be violated. There's something going on with the residuals, that as the predicted value is increasing, the residuals are more dispersed. So we don't want to see that, right? We want random order. Same thing here. We do see some pattern, not very major pattern, but we do see some pattern of material type versus the residuals. And so we ideally we don't want to see any pattern, right? But this video is mostly focused on how to make these charts. So let's go ahead and make these charts here. So okay, so now let's make that residuals versus predicted chart. So to do that, let's see, we have residuals here and predicted. They are next to each other, so I'm going to select these two columns, insert scatter plot, and here we have we can change the chart title. This is residuals versus predicted battery life, right? So let's bring this x-axis down at minus 80. So I'm gonna double click on y-axis. I'm gonna make the horizontal axis crosses the y-axis at minus 80. Okay, that's good. Then next we can what we can do is we can add the axis titles here. So let's go to chart design and quick layout, and maybe select the first one. On y-axis we have, what do we have on y-axis? Residuals. And on x-axis we have predicted battery life, and we don't need this here. So uh, if we just make this chart, looks like the residuals are randomly distributed across various predicted battery lives, which is good. That's what we would like to see, right? That means the assumption on constant variance based on this plot is not violated. So that's just one of the plots, and these are the two more. If you want to just make a couple of plots, one would be the normality plot on residuals, and the second would be this residuals versus predicted battery life. Okay, but we can make more charts to see some other interesting patterns in our data if there are any. So next chart would be temperature versus residuals. So I'm going to select the temperature here, and Control key press and hold, and we check the residuals. Okay, and let's make a scatter plot of these two. So there is some appearance of funnel there, which is so we need to look into it, right? Why the variance, the residuals are distribute, the variance is higher on this side as compared to for these two groups. So first, let's make the chart title here: residuals versus temperature. And let's make the x-axis cross y-axis at the bottom. So horizontal axis crosses y-axis at minus 80, and then we can add the axis titles here. Y-axis is basically residuals, and x-axis is temperature. Okay, and since we can even change the x-axis scale, because we know that we have only uh, three temperatures, right? So 20 degree, 70 degree, and 125 degree. So we can, if we want, we can change that x-axis scale, but it's okay. It's a quantitative variable, so it's all good. As you can see, as I was saying before, at low temperature, 20 degree Fahrenheit, our residuals have more variance, higher variance as compared to the 70 degree Fahrenheit and 125 degree Fahrenheit. So that is something to look into. But that's one chart. Okay, let's put this chart somewhere. Let's move it somewhere else. You can organize this nicely afterwards. I'm just trying to get it out of the way. So I put it here. Now the last chart that I want to make is the material type versus residuals. So exactly same procedure. You select the column, two columns, material type, control key press and hold, and residuals. Insert, scatter plot. The chart title is residual versus material type. Uh, you can fix your axis, make it cross at minus 80. And here, last time I said x-axis scale was okay because it was a quantitative variable, temperature was a quantitative variable. Here we cannot have 0.5 and 1.5 because the material type is not quantitative variable. We have basically three material types, and they are not quantities, they are different material types. So we may want to fix our scale. Minimum, if you, zero can be fine, but if you like to do one material type there, maximum is 3, and increment should be 1. Or if you don't like that to go on y-axis, here you can put a 0 there. And here we are, right? One, two, three material types and residuals on y-axis. So let's add the axis titles here. So axis title, y-axis is residuals and x-axis is the material type. So this is our last chart, right? And we also see some funnel shape here. So that is something to look into. So here, that's how we perform a residual analysis in Excel. It's a quite a work because you have to first of all you have to reorganize your data in this fashion for different problems. The idea here is to have all response variable values. In this case, there are 36 battery experiments, right? 36 different values of battery lives. There should be those number of rows, and then you have to list out each combination for that experiment. Material type, what like two factors, right? In this case, material type and temperature. So you have to list out every combination separately, and then you have to calculate the predicted value. uh, Predicted values can you can get those from the averages from your ANOVA analysis. Then residuals is basically the difference of these two, actual minus predicted. Then we have to sort them in ascending order. We have to give them a sort rank, and then we have to use this formula here for percentage cumulative probability. And once we have those data, we can plot these interesting residual charts for residual analysis. So that is that. Now next thing is performing the post ANOVA comparison of means, and we can go back to sheet one. We can perform it on sheet one here, and as I said before, we are going to perform a Tukey test. Uh, you there are, as you know, there are many post ANOVA comparison of means test you can do. Like for example, there's a Fisher LST test, or you can do simply t-test between each uh, plate material. In this case, you can perform t-test between two levels of the factors to compare the two groups. We will perform Tukey test. So let me pause video here. So let's talk about in general about post ANOVA comparison of means. So what ANOVA told us is, Uh, if you look at this ANOVA table, what we understood from the table is, for example, factor material type is significant, right? That means there are three different material types. So the null hypothesis is rejected. Null hypothesis of equality of means. Mu1 is equal to mu2 is equal to mu3 is rejected, and alternative hypothesis is accepted. That means there are inequalities. The mean battery life from three different material types is different, right? There are differences, but we don't know which material types are different. ANOVA table only told us that there are inequalities, right? That means either one or more material types are different from each other in terms of their impact on the battery life. But it did not tell us which specific ones are different from each other, and or which material types have no differences. So to find out those individual differences between material types, we need to perform post ANOVA comparison of means, right? We need to compare two at a time, and in this case we are going to perform a Tukey test. So let me write down here Tukey test. Now, one thing I would like to say before we work on this Tukey test is uh, because we in our analysis of variance we have also found that uh, the interaction between material type and temperature, the interaction effect is significant. So while performing the Tukey test to compare the pairwise comparison of different material types, uh, because the interaction is significant, it can interfere with our Tukey test. So one way to stop the interaction effect interfering with our Tukey test, what we can do is we can perform Tukey test, and we can perform Tukey test for material type as well as we can perform Tukey test for to find the differences between temperatures. But right now I am talking about Tukey test for material type. So one way to stop the interaction effect from interfering with our Tukey test for material type is to conduct the test at a specific temperature level. For example, 70 degree Fahrenheit, right? So that way by keeping the second factor fixed, in this case 70 degree Fahrenheit, we can stop the interaction effect interfering with the Tukey test for the material type. So I hope you understood what I'm trying to say here. So we're going to perform the Tukey test at a specific temperature level 70 degree Fahrenheit. So we need to write down a few things before we do that. First of all, we need to write down the K, which is basically the number of the different factor levels, and we are talking about material types. So we have three different material types, right? So K is equal to 3 factor levels. Next is n observation, number of observations. So number of observations for uh, each level we perform. If you look at the table here, we perform 4 experiments for each plate type at 70 degree Fahrenheit, because we are only doing it at 70 degree Fahrenheit, right? I may write down here. Okay, if our interaction effect was not significant, then we wouldn't care about this. We would perform at all temperatures. So in this case, because of the significant interaction effect, we are performing at 70 degree Fahrenheit. So number of observations for each plate type, we perform 4 experiments. So number of observations would be 4. Then next I want to write down degree of freedom for error and mean square error. So degree of freedom for error and mean square error. Degrees of freedom for error, we can get that from our ANOVA table, right? That is 27. And mean square also we can get from our ANOVA table, which is this. So I'm just going to copy 27 here and put it there. Mean square error, copy it and paste it here. Now we are going to perform individual comparisons between the different material plates. So we have 3 different material plates and we are comparing 2 at a time. So how many different comparisons we can make? 1 versus 2, right? One material type 1 versus material type 2, 1 versus 3, and 2 versus 3. So we can perform 3 individual comparisons. If this was easy because we just have 3, so we could figure that out. But if we have more number of factor levels, then the number of comparisons between individual factor levels, they can grow exponentially. So we can use uh, something called as combination to calculate how many individual comparisons we need to perform. So that will be equal to, if I go to formulas and I select math and trigonometry group here, there is a function called combine, right, which returns the number of combinations for a given number of items. So that will tell us how many individual comparisons we need to make. So we have three different material types, and we are comparing two at a time. So that means we have a total three comparisons. Okay. And finally, we need to find Q value, and then we will create a table: comparison, absolute difference, critical value, and result. So, so as we said, we have three different comparisons. So one would be 1 versus 2, material type 1 versus 2. Then second would be 1 versus 3, and third would be 2 versus 3. So these three comparisons we have to perform. Maybe I will make this bold here. And absolute difference is when we take the average of the four observations of battery life for material type 1 at 70 degree Fahrenheit, and we take the average of four different battery lives at material type 2 and 70 degree Fahrenheit. What's the absolute difference between those two averages, right? And is that absolute difference, so we are basically comparing mu1 versus mu2, mu1 versus mu3, and mu2 versus mu3, and we're going to find those absolute differences, and then we are going to decide, we are going to compare those absolute distances with some critical value based on this Q value, and based on that comparison we will be able to say whether the difference between mu1 and mu2 is significant or not. If it is significant, that means mu1 is not equal to mu2. If it is not significant, that means mu1 is equal to mu2. That means there is no difference between material type 1 and material type 2. So let's first calculate the absolute difference. So that is, uh, okay, we're going to use ABS function. Absolute returns the absolute value of a number, ABS function. And we need to take the difference, let's see, material plate 1 70 degree Fahrenheit, this average 57.25, average of those four observations of battery life, minus 1 versus 2, right? So we're going to look at, and 70 degree Fahrenheit, we're looking at 70 degree Fahrenheit, so this average 119.75, and then we close the parenthesis, and this is our function, right? Absolute value of that, so that's 62.5. Then 1 versus 3, so absolute value, let's see, 1 versus 3, so here is the 1, right? Average value 1 material plate 70 degree Fahrenheit minus 3, so here is a material type 3 and 70 degree Fahrenheit, this average, so that gives us 88.5. And last is 2 versus 3, so absolute value of the difference between 2 versus 3, mu2 minus mu3. So mu2 is this average, material plate 2 70 degree Fahrenheit column and average mu2 minus mu3, so that, close the parenthesis. So that's the absolute difference, right? Now to find the critical value, first we need to find the Q value. So to find the Q value, you need to basically look at the Tukey tables. You can find, if you search, just do a Google search, you can find the Tukey table easily. So I found one here on realstatistics.com. So if you just look at this studentized ranged Q tables, they're called, right? And they provide the critical values for Q at K degrees of freedom and alpha, and we will use alpha 0.05, right? So this first table is at alpha 0.1, so we don't want to use that. We want to use alpha level, the significance level of 0.5%, right? So I'm going to look at alpha is equal to 0.05. Our K, the number of material types or number of samples is 3, and degrees of freedom for error is 27. So we look at K is equal to 3 and degrees of freedom for 27. Okay, so 3 and 27. So we get 3.506. Now, sometimes some tables, Tukey tables, may not have value refined at, they may have like a 25, 30, 35. So you may not find exact 27. If that is the case, if you don't find exact 27, then you should select the degrees of freedom less than what you have. That way you can have a more conservative test. But since I found perfect 27 degrees of freedom here, so my Q value is 3.506. So I'm gonna type that 3.506. Okay. And now how do we find critical value from that is basically equal to Q times square root of mean square error divided by I believe divided by number of observations. So that's 4, and that gives us 40.55. I have it in the book also open here. So you're right. You can look at this. The critical value is Q value at alpha 0.05, 3 uh, three material types, 27 degrees of freedom, square root of mean square error divided by n, which is 4, number of observations. So that's good. And that critical value is same for the other two comparisons also, equal to Q value times square root of mean square error divided by number of observations. And once again, Q value multiplied by square root of mean square error divided by number of observations. If you want to just narrow it down to two decimal places, we can do that as well. Okay. So we are going to, now we have these critical values, we can compare our absolute difference with critical value. If our absolute difference between 1 and 2, mu1 versus mu2, if it is higher than the critical value, that means this difference is statistically significant. That means these two material types uh, are different from each other in terms of their impact on the battery life, right? So we can write it like this: if absolute difference is greater than critical value, okay, then we can say means are significantly different. If the condition is false, if the condition is not true, if absolute difference is not greater than the critical value, then means are not significantly different. Okay, so yes, absolute difference is higher than the critical value. That means mu1 and mu2 are significantly different from each other. That means there are differences in material type 1 and material type 2 in terms of their effect on battery life. And then we can just autofill this. Material type 1 and 3 are also different. Mu1 is that is also inequality statistically significant. So mu1 is not equal to mu2. Mu1 is not equal to mu3. But let's look at 2 and 3. 2 and 3 absolute difference is 26, less than critical value. That means there is not much difference between material type 2 and 3. There is not statistically significant difference between material type 2 and 3. Means are not significantly different. So that's how you can do pairwise comparison of means post ANOVA, because ANOVA doesn't tell you which means are different from each other. It just tells you that one of them is different, and you need to perform post ANOVA comparison of means only if your ANOVA tells you that there are significant differences in material types or significant differences in whatever factor in the context of the problem. If it says that the factor is not significant, that means all of the means are same. Then you don't have to perform the post ANOVA comparison of means. So that's how you perform Tukey test. So I will stop here. It's already getting a long video. We learned three things to summarize. We learned three things: how to perform two-factor analysis of variance in Excel. Second thing, how to do the residual analysis in Excel. How to plot those residual plots, normality plot, and the uh, plot of residuals versus predicted values and other plots. And finally, how to perform Tukey test in Excel. So thank you, and I will stop here.